I have HW plus the back side is another HW plus this side, which is 2W times H, right? So 2WH plus this side over here, which is also 2WH. Make sense? So the sides together, how many, HW, WH, same thing, right? 1, 2, 4, 6 of them, right? I have 6 WH makes up the sides. Make sense? Now what about the base? What's the base? What's the area? In these, I'm talking about the areas only right now.
W
right?
times 2W.
It's W times 2W, which is 2W squared. Okay? So the area of the sides together is 6WH. The area of the base is 2WH. Yeah? Now the cost. It's $10 per square meter to build the bottom and $6 per square meter to build the sides. So when it comes to cost, I'm going to call it C. I'm going to have to pay $10 per square meter for the base. So I multiply this times 10. So 10 times 2W squared plus, then I'm going to have to pay $6 per square meter for the sides. So 6 times 6WH, or HW. And this gives you 20W squared plus 36WH. And this is your cost objective equation. Make sense? So I think we're all up to that point, right? Our objective equation does not have a single variable in it. It has two variables, W and H. What we have not used yet is that this thing needs to hold 10 cubic meters. Okay, so let's do that now. May I erase?
Yeah.
Okay, so now this is our objective equation. Let's put the constraint. The constraint is that my volume must be 10, right? But the volume of this box is length times width times height, right? So W times 2W times H. So W times 2W times H must be 10, which means that 2W squared H must be 10. And I can solve that equation for either W or H. It's up to me. I'm going to solve it for H because it's easy. No, easier. I don't have to take square root. So H is equal to, divide both sides by 2W squared, and you get 5 over W squared. That's what you had done over there. You just had the wrong, you forgot the cost in there. I think that's what it was. So now I'm just going to replace the only H I see here with that. And that will give me my objective function as a function of a single variable. So my cost is now a function of just W. It is 20W squared plus 36 times W times 5 over W squared. Just replacing the H with 5 over W squared. And that should clean up a little bit. 20W squared plus 180 over W, right? Over W. Hold on. I'm multiplying. One of the W's cancels, and then I multiply this and this. Oh, yeah, okay. I worked this on the board in the other room, and I was like, I just didn't remember seeing this, but yes, this is right. Okay. You ready? That is our objective function, the single variable domain. So think about W. It can't be 0, right? and can be as big as we want. Be a really wide box, very narrow. So 0 to infinity is our domain. And so I'm going to need to do open interval methods. So critical numbers, number line, test points. All right, here's my derivative. Uh, 40w minus 180 over w squared. So we've done this a few times now, where we've had to take derivative of this. So bring the w up as w negative 1, bring negative 1 out, right? Okay, I'm going to get a common denominator. So I'm going to multiply the top and bottom of this by w squared. That'll create, what, 40w what? Cubed minus 180 equals w, or sorry, over w squared. Something seems off. Set that equal to 0. I'm going to go look on the other board. I didn't erase it. Oh, that's right. Okay. I just didn't remember seeing it.
Oh, with the front.
Okay. Yeah, so you just set the top to 0. 40w cubed minus 180. So move the 180 to the other side, divide both sides by 40. So 9 halves. 9 over half. 9 over 2 when you divide both sides by 40 and reduce. And now you take square root, or cube root. So w is the cube root of 9 halves. Okay. That's the only one we have, right? Because never undefined, well, it's undefined at 0, but 0 is not in our domain. So we're going to do a number line, and we're looking for down and up, aren't we? Because we're looking for a minimum cost. So we go to cube root of 9 halves. I'm pretty sure that that 1 is to the left of this, right? Because this is, yeah, 1 should work. And then I'm going to go with 9 because I know 9 is bigger than that. And I'm plugging those into the derivative. 1, get negative. Cost goes down. I just plugged 1 in here real quick. Right there. 40 minus 180. It's negative. And then you plug in 9. You should get up. All right. It wants the minimum cost, right? Find the cheapest box. It's not asking for dimensions. It's asking for the cheapest cost. Well, this is where we have the cheapest cost, right? So you're going to take this answer and plug it into the cost function for W, and that will give you your cheapest cost. I would just do it as a decimal. While you're doing that, I'm going to graph the cost function. The cost function was 20w squared, not w, sorry, got to use x, plus 180 over w. God, did w again, x. So this is a good example of how technology can help you, but if your viewing window on your graphing software is not, you know, if it's set up as its standard mode, then you're probably not going to be able to see the graph very easily. You're going to have to mess with things. So I'm going to try and bring this scale down. There we go. Okay. That's the graph, right? And I'm going to just click on it, and it's going to give me that lowest point. And look at that right there. Did anyone do 9 halves cube root and get 1.65?
Yeah.
Okay, there it is, 1.651. And this is the actual cost, $163.54. So if you're going to build a box this way with a volume of 10 cubic meters where the length is twice the width and it's $10 per square meter for the base and $6 per square meter for the sides, then you build it in such a way that this is W. So once we know what W is, we know what L is, right? L is twice that. So if I had asked you for dimensions, we know this is 1.651. We know this side is double that, right? So 2 times 1.651. And then what about H?
5 over.
It's 5 over that squared, right? So that would be this number here. 5 over the, bless you, 1.651 squared. Those would be the dimensions. And if you check it, if you take this number times that number, you should get 10. Right? Shouldn't you? Watch, it'll work. 1.651 times 2 times 1.651 times 5 over 1.651 squared, right? All those together should be 10. Those two cancel with those two. 2 times 5 is 10. Yes, today it does. All right, so you can see, I hope with this example, you can see how in the real world, when you're manufacturing things, you're trying to minimize costs, you can really use this, right? I imagine that the people who are getting paid to optimize these things are not doing the calculus, they're getting the function, right? Once they have the function, you go to the computer, right? Because that's all I had. That's all I needed to know is what that point was right there. Okay. That was fun, huh? It was fun, right? Looking at the time here. There's so many good problems in this section that I'm tempted to do one more. Or I can give you the review, right? Give you the review. There's a classic problem in this section that I feel like I just have to show you, or else I won't feel as if you've seen calculus appropriately. So let's try and do it. All right. I know I'm going to try and knock it out and leave us 10 minutes. Okay. So it's in the book, but I'm just going to put it on the board. So what you have is a right cylinder, okay, and it has a radius of capital R, and it has a height wait a minute, hold on. You know what? Hold on. Back up. Stop. Restart. Sorry. I'm sorry. I'm sorry. There's two, and I started writing the wrong one. Yeah, let's do this one. We have, instead of that, we have a cone. Okay, we have a cone. All right? And this cone has a radius of capital R and has a height of capital H. All right? This cone is fixed. It's not changing. There it is. All right? This is fixed. What I'd like for us to do is I'd like for us to inscribe into this cone a right cylinder. So let me draw it first. I'm going to put a right cylinder in here that just touches the cone up there and then comes down and touches the base of the cone like that. Do you see it? It's a cylinder, it's a beer can inside of a cone. Yes? There's many ways I could do this. If I were to draw that cone again, there's the cone again. I could have made this cylinder like this. Just touch up at the top, like that. I could have done this as well, right? I could have also done maybe another extreme where I make it really, really wide, like this, right? Do you see the different scenarios there? If the cone is fixed, I want us to find the dimensions of the right cylinder that has the most volume. So find dimensions of a right cylinder with maximum volume. So it's like I'm trying to pack a cylindrical object into a conical object, right? I'm trying to insert a insert a cylinder into a cone shape, and I want to do it in a way that I can get the most volume of the cone that I can get. Make sense? All right, so let's start doing it, all right? So what is the objective? Do you all agree these have different volumes? These should have different volumes, right? There's some optimum solution. The taller you get a bigger height, but it's narrow, right? And if you go wide, then it gets short, right? So there's some optimum way of doing this.
Was there any constraints given? Or do we have to find?
There are no constraints given. That's it. Yeah. So the constraint is within the problem. We just need to figure it out. So what's the objective? What are we trying to do? Maximum what? Volume of the cylinder. Right? You said cone. Right? The objective is to get maximize the cylinder's volume. Okay, well, then we're going to need the formula for the volume of a cylinder, aren't we?
Yeah.
So the volume of a cylinder isn't it pi r squared h?
Yeah.
Now, when I write pi r squared h, I am referring to little r and little h because the cone has its own radius, doesn't it?
That's capital H and capital.
It's capital H and capital R, right? When I'm referring to the volume of the cylinder, I'm referring to this R from here to here and this H from here to here, right? These aren't the same things, are they? Capital R is the radius of the cone, capital H is the height of the cone. Okay, so we're trying to maximize that. It has two variables in it, R and H, so I need a constraint. This is the tough part. What's the constraint? So all of our constraints that we've had up to this point have come from some part of the word problem, right? But the constraint, what it was an equation that had these two variables in it, right? So like r and h or x and y, and then we were able to solve for one of the variables, right? Like in the previous problem that y'all just did, you went and solved for h, didn't you? Yes?
It's going to be like little h can't be bigger than big H, and then little r can't be bigger than big R.
So that would be more of a domain restriction, right? Like we do have some restraints on little r, right? Smallest it could be with 0, and the biggest it could be with big R, right? But that's more of a domain thing. What I need is to somehow connect little r and little h together with an equation so that I can solve for one of them, right? You understand?
Could you subtract the cone volume from that?
Subtract the cone volume.
Because the cone is going to be bigger than what's left is the cylinder, right?
Mm-hmm. But I'm not sure how that gives us, how does that give us an equation? All I want is an equation with little r and little h in it.
On the same side,
Anything.
or-
An equation with both those letters in it, little r and little h, any equation. Remember, capital R and capital H are just fixed numbers, right? Imagine that this is 6 and that's 10, okay? These are numbers, right? So, like I said, this is a problem where you have to see it, all right? Like, classic problem. So what I'm going to do to come up with my constraint, which is not very natural, that's why we're here, is I'm going to draw you a new picture. I have a question right now. I just don't know how hard y'all want me to push you on this. I have an option. I can leave these as just constants that we don't know, or if you think it would make the problem easier for you to understand this first time through, I can replace these with numbers.
Let's do constants we don't know.
You want to stick with constants you don't know? Okay, we can do that. All right, but just remember these are numbers, right? So what I've done over there is I've drawn this picture. If we were to slice it down the middle, take a cross section and open it up, I'm looking at it from a cross section view, all right? Let's label some things over here. Let's see. You know what? Let's cut that down the middle. How about we do that? Cut that down the middle. And let's look at this. Let's just look at one side of it. I don't know what we're going to use yet. Let's see what we're going to use. Do y'all see? All I'm doing is looking at one side of it. Let's start labeling things. What's the distance from here to here? Little r. What's the distance from here to here?
R.
Big R. Right? What's the distance from here